All right, so here we go. Today we get to talk about energy and Kepler's laws. All right, so I guess before we do anything, I just want to remind you of a couple things that we've learned prior in the year. We're going to be dealing with energy, and so I want to, I guess, remind you about a couple sort of fundamental energy rules we've learned. So remember that if you have a non-conservative force, if you calculate the work done by that non-conservative force, that tells you the change in total energy of the object. If you have work done by a conservative force, that tells you the change in potential energy associated with that conservative force. But remember, you got to flip your sign on it, right? That if you gain gravitational potential energy, then gravity is working against you, right? And then finally, we talked about the fact that the net work done was just equal to your change in kinetic energy, which is the work energy theorem. Okay, so those are going to be relevant, and actually, honestly, a lot of what we're going to do in this section is just going to be kind of looking at some of these old concepts that we've learned about, but in terms of planetary, bodies and such. All right, so just a quick reminder. So this is something that came up, I don't know, when we were talking about gravitational potential energy. And we talked about the fact that gravitational potential energy is sort of stored in the gravitational field between two objects. So, if you lift a rock up to the top of a cliff or something, we usually say that the rock has potential energy. But technically speaking, the potential energy is stored in the gravitational field between the rock and the Earth, okay? So it's a property of the pair of particles, not necessarily just the rock. Okay, so it doesn't really make sense to say the rock has potential energy. We say that the rock-Earth system has potential energy. And so you can't really divide it up and say some of the energy is the rock, some of it is the Earth. It just is energy of the system, okay? Now we often, like I just finished saying, we'll often talk about the gravitational potential energy of just one object. And the reason that you can do that is because if you drop the rock or the baseball or whatever, it's the rock or the baseball that gains the kinetic energy, right? Because the Earth is so large that its velocity really doesn't change any appreciable amount, all right? So really you should only do that in systems where one of the objects is way bigger than the other one, okay? All right, so how do we calculate gravitational potential energy for a system of objects? So we have learned in the past, we've used this. Gravitational potential energy is mgh, right? Okay, but the problem is, as you get, like suppose we want to find the potential energy of the moon, right? Like the moon is orbiting the Earth, okay? Well, the acceleration of gravity out where the moon is, the acceleration due to the Earth's gravity out where the moon is isn't 9.8, okay? So what we're going to do is we're going to combine this equation with the fact that we know that g is the universal gravitation constant times the mass of the Earth over r squared, where r is the distance you are away from the center of the Earth, right? So remember, when we calculate GPE, we've always used h, and you just sort of decide where you want to measure the height from, okay? Well, what we're going to do is we're going to measure from now on, when we talk about planetary motion anyway, we're going to measure our height from the center of the center of the planet, I guess, would be the easiest way to say it, okay? So this basically is just going to end up becoming r for us, okay? And so what we get then is that the gravitational potential energy of an object when it's some distance away from the center of the Earth is m times g times r. So you get m times g times r, right? All right, and if you simplify that, obviously the r's here cancel out, and you get gmm over r, right? Okay, so but what that means is as your radius increases, your gravitational potential energy decreases, right? If you increase this, you're going to get less gravitational potential energy, okay? So this is a very frustrating thing. So it turns out that the equation that we're going to use to calculate the gravitational potential energy is exactly this. Let me clean it up a little bit since it got a little scribbly there. So our GPE for an object is going to be g times the mass of the two particles divided by the distance between their centers. but we're going to tack a little negative sign on there to indicate the fact that if you increase your radius, you're gaining gravitational potential energy. Technically, you're losing negative energy, okay? So here is our equation, okay? And notice what this means is as your radius gets closer and closer to 0, so the limit as r goes to 0 of u is what, negative infinity, right? So that's like the smallest gravitational potential energy you could have. And then the limit as r goes to infinity of u is 0, okay? So as you get the least potential energy you can have is at the center of, you know, your planet or whatever, and that would be a gravitational potential energy of negative infinity. And then as you get farther and farther away, the energy gets less negative and eventually approaches 0, okay? So this is a really confusing thing, just because of these negative signs. But you just, you know, you got to learn to work with it, I guess. There's no other way to do it. All right. So the little notes we've got here, note that the value is negative and it approaches 0 as r goes to infinity. The gravitational potential energy of a system. So suppose you've got a couple different objects. All right. So here we've got this. So we've got this. So suppose I want to find the gravitational potential energy of this system. Well, then what you have to do is you have to find the gravitational potential energy of the mass 1, mass 2 system. Find the gravitational potential energy of the mass 1, mass 3 system, and find the gravitational potential energy of the mass 2, mass 3 system, and then add them all up. Okay? So, now, remember that gravity is a conservative force, right? So it means the work done by the force doesn't depend on the path followed. Right? Remember, like if you lift a pen to the top of a mountain, the gravitational potential energy you give it doesn't depend on the path you took to get it there, right? And so there's a little graphic here. If we take this object, you know, and move it from here up to here, whether you just go straight there or you follow this, you know, crazy zigzaggy path, the work done by gravity is going to be the same, right? It's a conservative force. All right, and so remember that the change in potential energy is equal to the opposite of the work done by conservative forces. Okay, we already talked about that. All right, worth noting, if you take the derivative of this, right? Yeah, sorry, if you take the derivative of this, it gives you the equation for the force of gravity, right? Okay. All right, so that is that. All right, so it turns out this buys us a lot, okay? So suppose we have an object and we want to throw it or launch it at such a speed that it escapes the Earth's gravitational pull, okay? We have to launch it at what is called escape velocity, okay? So here's how this is going to work, all right? So suppose you've got an object on the Earth. So here's the Earth, all right, and here's my object, all right? And I want to launch it with some velocity so that it escapes the Earth's gravitational pull, okay? Well, what that means is by the time it gets to sort of a position of infinity, it still has to have at least a little bit of velocity, right? Because once you launch it, there would be, you know, the only force would be gravity, right? So what we need is the total energy at launch has got to equal the total energy once it gets out to infinity, right? Okay, well our total energy at launch is going to be the kinetic energy, which is 1/2 mv squared, plus the gravitational potential energy it has on the Earth, which is negative g times the mass of the Earth times the mass of the projectile over r. Okay? And what do we want that to be? Well, let's see. We want it to be at infinity. So remember, at infinity, well, here, let's just write it out. So we want our kinetic energy to be just greater than 0, right? So I don't know how we want to write this. I mean, 0 is the limiting point, right? So we want our kinetic energy to have just reached 0, plus our GPE. Remember, once your r goes to infinity, your GPE is 0. Okay? So what we're going to do is we're going to solve this, right? oh, well that means that so if this is all 0, right? This is all 0. So I get 1/2 mv squared. mv squared equals gmm over r. Notice the little m's cancel out. Multiply by 2, and we find that our v has to be 2gm over r, and then square rooted, right? So this number is what is known as the escape velocity, okay? And it represents the minimum velocity that an object has to be launched at to escape the gravitation of a planet or whatever. Also worth noticing, the direction doesn't matter. This will work in any direction. You can fire something, I guess you couldn't fire it at the surface of the planet, but as long as you're firing it sort of away from the, here. So here's the planet. So you can fire it this way, or this way, or this way, or this way, whatever. As long as you're launching it, any velocity above this, and it will escape the planet, okay? And so that is called escape velocity, all right? And on Earth, like when they launch rockets, they launch them from near the equator always, right? And they launch them eastward to take advantage of the Earth's rotational speed, okay? So what is the escape velocity of the Earth? Well, here's a little data table that gives us different escape velocities from different things. So on the Earth, escape velocity is 11.2 kilometers per second. To escape the moon's gravity, 2.38 kilometers per second. Okay? And you can see there's a whole bunch of other ones here. Okay? All right. Okay, so take a second and read this little checkpoint here. See if you can come up with an answer. Pause it, maybe, and answer it. Okay, I'm going to assume you have paused it. And let's answer this. All right, so you move a ball of mass m away from a sphere of mass m. So you've got a ball here, so you've got a big sphere of mass m and a ball of mass m, and you're going to move it away, okay? You're going to move it from here to here. So. Okay, and the question is, does the gravitational potential energy increase or decrease? Well, so if you think of the big sphere as being the Earth and the little sphere as being a ball, basically you're increasing the height of the ball, and so our gravitational potential energy ought to increase, right? In terms of our equation, here's what's happening. We're moving it from a starting position of, let's call this distance little r, and then you're moving it to a bigger distance, which we'll call big R, right? Okay. So, let's see. So our GPE initially would be gm over r negative, right? And our GPE final is negative gm over big R. So when we do our change in GPE, it should be GPE final minus GPE initial. So it's negative gm over r minus negative gm over little r, right? So this is going to be a small negative, right, because this is a big radius, and then we're subtracting a bigger negative. So minus and negative becomes addition. That's going to give us a positive answer, right? So we're gaining gravitational potential energy. Okay, so it jives with, what we learned in the past. All right, and so then is the work done by gravity positive or negative? Well, you're working against gravity, right? As you move it this way, gravity is pulling that way. So you're working against gravity. Secondly, remember that the work done by your gravity should be equal to the opposite of the change in gravitational potential energy, right? Okay. So, this one is increase, and this one is negative. Okay? All right, now, motion of the planets. So there was a dude who lived in late 1500s, early 1600s, named Johannes Kepler. He derived the three, or what are now known as Kepler's laws, and they describe the motion of planets around the sun, or moons around the planets. He did this using data collected by a guy named Tycho Brahe who was, if I remember right, a Danish astronomer. And he spent countless hours cataloging the motion of planets. I want to say he used Mars, but I could be wrong on that. I should have looked it up before I began these notes. But anyway, so before we get to it, so his first rule is this. I'm going to skip ahead a slide and then I'll come back. All right, so Kepler's first law is called the law of orbits. All right, and it says that all planets move in elliptical orbits with the sun at one focus point. Okay. Similarly, all moons move in elliptical orbits with the planet at one focus. Okay. So, in order for this to make sense, we need to learn a little bit about ellipses. Okay. So let's go back for a minute. So on this drawing here, we've got an ellipse. Okay. So you can see this blue dotted line represents the path of a planet. Okay. So here's our planet, going around the sun. The sun is here labeled. Okay. So notice there are going to be two focal points. There's one here where the sun is, and then the other focal point is just empty space, okay? And so the idea is, your planet is going to orbit around the sun, around like this in an elliptical orbit, okay? So some things that you need to be aware of. So first of all, let's label some of these things. So this guy here, the distance from the center of the ellipse out to the edge along the longest thing is what is called the semi-major axis. Semi-major axis. And it is denoted with a lowercase letter a. Okay? Now, this distance here from the focal point to the center, I don't know that it actually has a name, to be honest, or if it does, it is escaping me currently, but it's usually referred to as a lowercase letter c. Lowercase letter c. My voice just did something weird there. All right, and then we can calculate what is called the eccentricity of the orbit. Eccentricity, E, and it's simply the ratio between C and A, okay? And so you can see on the little drawing here, if you rearrange this, you see that C is equal to E times A, which is how they've actually labeled this little pink bit here, right? They just labeled it as E times A instead of even calling it C, okay? So there you go, all right? Now, it turns out that if your eccentricity is 1, then basically you're taking this ellipse and stretching it out until it becomes a line segment, okay? And if this distance here is 0, you're taking your two focal points and moving them both to the middle, and you're left with a circle, okay? So, an eccentricity of 0 corresponds to a circle. E equals 0, circle. You can remember that because a 0 is a circle. And if the eccentricity is 1, then your ellipse is almost a line segment, or is a line segment. And again, notice the number 1 is, in fact, itself a line segment. Okay? So that's how you can remember that. All right? So it turns out that most of the planets in our solar system have eccentricities that are pretty close to 0. Most of the orbits are almost circular. So there you go. All right, so that is Kepler's first law. The planets move in elliptical orbits. The sun is at one focal point, at one focus, and then there's just empty space at the other one. Okay? All right, law number 2 is called the law of areas. All right, so Kepler discovered that if you plot the motion of a planet throughout some time interval, suppose we look at a week, okay? So this planet in 1 week is going to move, say, from here to here. All right, and in doing that, it sweeps out this little, oh man, I need to calibrate my board. It sweeps out this little triangle here, and that triangle has some area, right? Okay, now, if we do that sometime later and map how far the planet goes in 1 week, so maybe it's here, and then 1 week later, it's going to be, I don't know, maybe over here. This is obviously terribly exaggerated, but it turns out that this area is equal to this area. All right? And this is called the law of areas. All right? So But what it actually what ends up being the case is this is exactly the same as the law of conservation of angular momentum, which means that the angular momentum of a planet as it orbits the sun at any initial point is equal to its angular momentum at any other final point. Okay? In English, remember, we can treat because the planets are so far from the suns, we can treat them as point particles. So remember, the angular momentum of a point particle is just mRV, right? So this means you can take the mass of the planet times the radius of the planet initially, as in orbit radius, times the velocity of the planet at that instant, and it's equal to the mass of the planet times the radius at some final point times its velocity at some final point, and the masses even cancel, right? So the radius times the velocity for a given planet is constant. And when I say radius, I mean the distance, the orbit distance, I guess. Okay? So this is a useful thing to know, okay? All right. Finally, Kepler's third law can be written a couple ways. So first of all, it's this. It tells us that the period squared, so here's how it's always written. This is Kepler's third law, all right? It's a mess, all right? So I always remember two things. I remember that the period squared is always proportional to the radius cubed, okay? So, for example, if you had a planet that was, suppose you had planet A and planet B orbiting the same sun, which is important, and suppose that the radius of planet A was this, and suppose the planet of radius B was twice as big. Okay? Well, that tells us something about their relative periods. So if this is the period of planet A, we ought to be able to figure out what the period of planet B is. Okay? And so the idea is the period squared is proportional to the radius cubed. So here I'm doubling my radius. So 2 cubed has got to be proportional to my period squared, right? Or my change in period squared. So 8 is proportional to t squared, so that means that my period is proportional to the square root of 8. So this should be root 8 times the period of A, okay? So double the radius gave us root 8 times the period, okay? Because they're both orbiting the same planet, okay? So that's kind of a quick shortcut, all right? Now, if that didn't make sense to you, then you can derive all this garbage, all right? So here's a really quick derivation of Kepler's third law, and it's actually not that bad, all right? So here's what we're going to do. We are going to start with the fact that we know that the velocity of a planet, assuming it's moving in a circular path, is 2 pi r over the period, right? Okay? So we also know that the acceleration of a planet is centripetal, assuming it's a circular orbit. Okay, if it's a circular orbit, we know that the centripetal acceleration is v squared over r, which is this thing squared over r, and we know that that's provided by gravity. So that should be the acceleration of gravity, which is just g times m over r squared, right? We learned that in the last video. Okay? So if I cancel out an r here and an r here, I get v squared equals gm over r. And now what I'm going to do is I'm going to replace v with this. And so you get 2 pi r over t squared equals gm over r. And then you can do a little bit of algebra and rearrange this and get this. Okay? So there we go. All right, now it turns out, and this is not obvious, but it does turn out that this law works as well if it's an elliptical orbit, but you just replace r with a, okay? And remember, a is the length of that semi-major axis, okay? So that is the relationship between the period of a planet and its distance from the sun that it's orbiting, okay? All right. Cool. And I think we already talked about checkpoint 4, right? I think we answered that, right? Larger period is also going to be the larger radius. And oh, we didn't talk about speed, did we? Oh, I guess we did. Sure we did, yeah. Because we discovered this. We discovered that v squared is gm over r. So that means the velocity of a thing in circular orbit is root gm over r. And again, if it's not a circular orbit, you can get an average velocity by replacing r with a. Okay? So, bigger radius, slower velocity. Okay, so now what happens is this. All right, so we just discovered that there is one specific velocity called v circ, which tells us the velocity required for an object to maintain a circular orbit around a planet or a sun or whatever at a radius r, right? Okay, so suppose this is our sun, okay, and I'm out here at a distance r away, okay, and I want to maintain a circular orbit. Well, that means I need to be launched at this velocity, v circ, and I'll maintain a circular orbit. Okay, that is a terrible circle. Deal with it. All right, now, so that dotted line there represents v circ. All right, now, what if our velocity is bigger than, or is less than that? So if our velocity is less than v circ, then what's going to happen is this. Our object will fall towards the thing that it's orbiting, in this case, the sun. All right, so if it's, well, so if it has no velocity, it'll just go straight down, right? But so suppose it's moving, but not fast enough to go in a circle. What happens is it sort of falls closer and closer to the planet, or to the sun. So notice here it's closer to the sun than it was over here. But as it falls, it goes faster and faster, and it sort of slingshots around and goes up like this, okay? Now, you know, it's possible that it could go slow enough. So here's another possibility, still going slower. You know, maybe it does one of these, and it could crash in, okay? I guess that, oh shoot. That was bad. I'm going to undo that. If it gets past this point, it's going to stay in orbit. So as long as it gets past that point, you're in good shape. Okay, so anyway, so if your velocity is less than the velocity required for a circular orbit, it has an elliptical orbit, like this little red shape that I just drew. And notice my other focal point is going to be here. So here's F, and here's my second focal point, which I'll call F prime. Okay? Now, if your velocity is bigger than the velocity required for circular orbit, but still less than v escape, then you get a bigger elliptical orbit, which will look like this. So now, here's my focal point from the sun, and then the other focal point would be out here. Okay, so the idea is it's moving away from the sun, slowing down, slowing down, slowing down until it stops and comes back. Okay? And then, if your velocity is equal to the escape velocity, then it'll just kind of, then it'll just kind of do this. Okay? And obviously, if it's bigger than that, then it goes even farther and farther away. So this would actually give you part of a hyperbola. Okay? All righty. All right, now, Let's talk about kinetic energy. So if you've got a planet in orbit around a sun, or a moon in orbit around a planet, we can talk about the kinetic energy. It's 1/2 mv squared. But remember, a minute ago we saw that v squared was gm over r, right? So substituting gm over r in for v squared gives us this. And notice that's negative 1/2 times gmm over r, right? So it's this, all right? So when you've got an object in circular orbit, it turns out that the kinetic energy is exactly half of the potential energy, but, you know, flip your sign around, okay? And so the total mechanical energy of our system is kinetic energy plus potential energy. Here's the equation for kinetic energy. Our potential energy, remember, is negative, so this is actually plus a negative potential energy, and it gives us this, which incidentally is negative kinetic energy, okay? So the total energy is, in a circular orbit, is just the opposite of the kinetic energy, okay? Now, it turns out that even if you're in an elliptical orbit, this works, but you just replace r with a, okay? So, or E equals negative gmm over 2a for an elliptical orbit. Okay? So, like I said, the total energy then, when you're in orbit, is always going to be the negative of the kinetic energy. If you're in a circular orbit, that's true. Because if you're not in a circular orbit, your kinetic energy is always changing, so that wouldn't make sense. All right, so let's see. Like I said, if it is an ellipse, you can substitute a for r in those equations to find your energy at a given instant. So the energy of the orbit, it turns out the energy of a planet's orbit depends just on the length of its semi-major axis. So all of these planets here in this little drawing here, they all have a semi-major axis of the same length, okay? So let's see. So this black one has a semi-major axis that is this long, right? The green one is, I don't know, something like, I'm trying to find the center of it, something like this. And the red one is something like this, right? So those are all about the same length, and so they all have the same amount of energy, okay? So that is a big, big idea, that the length of that semi-major axis determines the total energy, and it is given by this, okay? And so then at different altitudes, you can find the gravitational potential energy, and then the remainder of your energy has got to be kinetic. Okay? All right. Cool. I guess that's it. All right, so this is one of those homework assignments where you just gotta kind of dig in. I'll be honest, before I started teaching this class, I had not done this a ton, which is honestly part of the reason these notes are a little sketchy. But I think if you start working through the problems, they'll start to make a little bit more sense. Okay, so real quick, main ideas are those couple equations. I find myself going back to this a lot. Okay, this is super important, that your energy is determined by the length of the semi-major axis. You definitely need to know this V-circ equation, and Kepler's law. Please remember that it can be derived fairly easily just by using circular motion and centripetal motion, or centripetal force equations. Centripetal acceleration equations, I guess. Make sure you remember this guy. If you know the velocity at one point, you can always find the velocity at another point by using conservation of angular momentum. And then obviously the equation for potential energy and escape velocity. Okay, so that escape velocity equation is right here. 2gm over r square root e. And potential energy is this guy. All right, there you go.